Julia Matevosyan. I'm a chief engineer at ESIG, and I have a pleasure chairing the session today, which is on transmission interconnection process. And we have 5 presentations today. They are kind of different topics, but all related to transmission interconnection process. They are also global. We have Canada and Australia and some US presentations here. I think I haven't missed anyone. That's right. And independent state of Texas, of course. All right, so the first one is Anton Stepanov. He is a research and development specialist at EMTP, Canada. He was participating in the EMT tutorial yesterday as well and presented an EMTP tool. And today he'll be presenting on grid forming battery application for weak grid conditions in Chilean power system. So Anton, the floor is yours.
Thanks, thanks a lot, Julia. So I am going to put it in the pocket. All right, so good evening, good afternoon, everyone, and welcome to this presentation on the GFM battery application for weak grid conditions in the Chilean power system. So this presentation probably would be among all the presentations in the session with the least appropriate, because there is not so much information about the actual interconnection process, but it's a grid forming converters and it is connected to the grid, so there was some interconnection process involved, at least in theory. So anyways, let's start with a brief overview of the Chilean grid and how it works and what are the governing bodies. So the study that I'm presenting here was done jointly by this CEN, Coordinador Eléctrico Nacional from Chile, and EMTP. So what is the CEN organization? It is an independent technical organization which is responsible for reliable, secure, and economic operation of the Chilean grid. It has many functions which are similar to what a typical TSO would have. So they are responsible for secure and economic operation of the power grid, open access to the transmission system. They administer the markets for energy, power, capacity, facility services, all that. They take care of the expansion of the transmission network and planning. They actually are the ones who manage the interconnection process and do all the studies involved in this project, in this process. And well, there's a long list of things that they do. A couple of words about the Chilean grid. This is a very unique, I would say, transmission system because it is a radial, very long radial transmission network. We are very used to meshed grids with loops everywhere, but this is a essentially long radial transmission, 500 kV transmission system with also several loops in the 220 kV level. It's mostly interconnected, but in the southern part of the country, you have islands which are not connected to the main grid. Also, another very particular thing about the Chilean grid is that there are some points which are very, very weak. Like there were presentations yesterday mentioning that, well, it's not very good to have ECR below 3. Well, the reality of the Chilean grid is that they actually operate with short circuit ratios below 1.5. So that's something you have to deal with. And because of the way the network is built, because of the way the generation and production, well, generation and consumption of electrical power energy is in the Chilean network, there are congestions that happen often in the transmission system. So why are there congestions? We have a lot of generation, solar generation in the northern part of the country. So keep in mind that Chile is in the southern hemisphere. So north is not where it's cold. It's actually closer to the equator. So you have a lot of sun and there is a desert in the northern part of Chile. So there is a lot of solar generation. There are many PV plants and they have a relatively reliable operation. They produce a lot. Then you have consumption centers, which are near the capital of Chile, somewhere in the central part of the grid. So you have a large quantity of electrical energy coming from the northern part to the center, center-south as well. Then you have the wind generation and also hydro generation in the northern part of Chile. All right, so a couple of words about the system and the distribution of the generations. On the left, you have the installed capacity. So you have roughly comparable sizes of PV generation, wind generation, gas, well, let's say thermal in general, gas or fossil fuels, and hydro. Then on the right, you have the actual generation, not the installed capacity, but the actual generation, and it somewhat corresponds to what you have, on the left. Mostly all the installed generation units are working. You can probably see the only significant difference in the diesel generation. They're not used as much. Otherwise, it's kind of comparable. Now, there is one question you might be asking: how can you actually measure energy generation in megawatts? Because it's 83,000 megawatts. Well, the question, well, the answer is basically a typo. So sorry for that. It's gigawatt hours. All right. Now some statistical data. So here it's basically the same information, but with numbers. We have the installed capacity of 33 gigawatt roughly, and the generated energy is 83,000 gigawatt hours, with a peak demand of almost 12 gigawatt. So this is the normal numbers for 2022, and it is somewhat comparable in 2023. The statistical data that we have ends in July, so that's where this data was collected. So I don't have the latest results, but it should be comparable to the 2022. Now, one thing you can notice here is the share of the variable renewable energy sources. So the peak numbers for 2022 was, I don't know if my mouse is visible there. Yes, okay. So it's about 68%, and in 2023, it got to 71%. So in a grid as large as this, they actually were able to function, to operate with more than 70% of renewable generation, and well, it worked. They're also considering including batteries. It's not yet implemented, but the project is, let's say, well, I'm not sure actually if construction started, but it is an ongoing project. Now, typical daily generation profile. So you have two sets of data here on the left, the working day in July, which is winter in Chile. Again, it's southern hemisphere. It's not summer, it's cold in July. And well, hopefully you can read this small font in the bottom. But what it shows is that you have obviously the large peak in the PV, and the rest is roughly stable throughout the day. What you may not clearly see here is that the dashed lines show you the marginal costs. And in the graph on the right, you can see that marginal costs of PV generation during the day in January, which is summer, is basically zero. So let's say zero marginal cost for energy. It's very, very good. You want to have more? There you go. Okay, so here is data with a slightly different format. So here you have this pie chart with roughly the same data that we saw in 2022. So if you're hungry, probably you will like this pie chart more. And on the left, you have the typical marginal cost distribution throughout the week. You have periods of the day when, the midday where the marginal costs are going to zero or almost zero. And then at night, it increases to some more larger values. All right, this slide, I think it could be interesting to know, like, what is the daily, day-to-day generation of renewables. So here for each dot at the top represents 1 day and the share of renewable generation. And the this one dot on the right that is marked 1% VRE is the one that we discussed at the very beginning. This is the peak renewable generation in 2023. So they were able to operate this point for 3 hours. But you do see that throughout the year, there are periods where you have almost zero renewable generation. So that happens. And you also have at the bottom the curtailment of the VRE. And you see that around February, okay, I don't know if you speak Spanish and you can read these small fonts, but basically this part of the graph shows the January, February period where you have the largest share of VRE curtailment. Probably it is related to climate. They didn't really explain why it happens more in that period of year, but should be related to the climate conditions. All right, and now a little bit more about the plans of the Chilean grid for the future. They want to have 100% renewables in 2030. They want to achieve decarbonization by 2040 and then carbon neutrality by 2050. Ambitious plans. There's not so much time left until 2030, but the progress is there. There's a lot of ongoing projects for renewables going on. Hopefully, they are going to achieve it. In the short term, the project that is being implemented right now is they want to include synchronous condensers in the northern part. So this is the part where they have a lot of solar generation and not necessarily so much consumption. So a lot of converters, and they want to improve the stability of that region. Okay, well, there are some challenges which are typical for many grids, not only the Chilean one. The daily variation of renewable energy sources, the weak grid, the management of the ramp, the famous duck curve, where you have a large peak in the required power. And there are some solutions that they are looking at and are implementing it in their grid. So there is an HVDC transmission between two substations that is being built. They're also considering building the battery systems, including grid forming inverters and other components. All right, so the second part of this presentation is going to be on the study that was performed by the CEN and also in part by us at EMTP. I'm not author of this paper. Unfortunately, the people who were actually authors couldn't make it today, but I'll do my best to present this study. So let's start with the model. So we modeled, well, actually the Chilean company CN modeled the transmission grid at 500, 220, and 110 kilovolt level in EMTP with roughly 8,000 nodes, many control blocks, many models of renewable generation. Some of them were homologated with manufacturer data. Some of them were generic because of sometimes lack of data, sometimes lack of time. And the backbone of the Chilean transmission system, as we mentioned at the beginning, is the 500 kV transmission line that goes from the north to roughly center-south region. Right, so what was the objective of the study? Is to model grid forming converters in the grid and assess their basically dynamic behavior in the case of very high level of renewable generation, 70% in particular. So they installed GFM converters in 4 locations with very low short circuit ratio. So the points where they need the most support. And the contingencies that were studied are basically 3. The worst N-1 fault, islanding, and the loss of the last synchronous generator. So they are only operating with converters in the island. Some generalities about the grid forming converters. So the way it was implemented in the paper is as follows. They used the generic primary control model and changed some parameters to achieve different types of control. The droop control, proportional to basically frequency deviation, the virtual synchronous machine, and the VOC. So pretty standard controls in the GFM world. All right, so the first test was to simulate a fault near a substation, which is called Polpaica. And this location is the worst in the sense that the faults here oftentimes lead to unstable grid. So depending on your operating conditions, if you have, let's say, if you're operating close to the transmission limit of the 500 kV transmission, it may lead to complete loss of the grid. If you are below the peak, it will lead to the largest frequency, well, largest swings in the generator angles. So, to line to ground fault at the 500 kV line, it is isolated by disconnecting a line, defaulted line. And here at the bottom, you see the results of the voltage, amplitude, and the frequency measured by a PLL. You can see that the frequency basically becomes unstable. The grid is not recovering after the fault. So the corrective measure number one that was tested is to include synchronous condensers with the total power of 1100 megawatt. They are not using GFM converters at this point. So they are installed in the same points that we were discussing previously. So the points where the short circuit ratio is the lowest, so the most, let's say, vulnerable points in the grid. System becomes stable, as you can see at the graphs in the bottom. However, the frequency, despite being stable, is not necessarily at 50 hertz, which is the nominal in Chile, but slowly recovers after the fault clearance. But it's already better than before. Now, the second test that they performed, so instead of synchronous condensers, they included the grid-forming converters with the capacity of 150 megawatt. They were operating at 100 megawatt before the fault, so there was some power flow before the fault. They were not just turned on as a corrective measure. So with all the three control modes that we were discussing at the beginning of the second part of the presentation, system is stable, we get very similar responses, and the frequency stabilizes much faster after the fault clearance. So we can see that with the much reduced capacity, previously we needed 1100 megavar for the synchronous condensers, and now it's only 600 megawatt, let's say, in the of the grid forming converters. All right, second test is, well, the third test is the islanding. Now, there is a fault which is disconnected. Well, actually, the fault clearance is basically disconnecting two lines of the 500 kV corridor. And in this case, you basically have two independent islands, one in the north, which is smaller, and one in the south, which is larger and has a lot of synchronous generators connected, so there are no problems with it. However, in the north, you only have about 3,000 megawatt generation and only one synchronous generator unit. So as you remember, in the north, you have PV, and basically that's it. However, with the grid-forming converters, they were able to stabilize this island without any problem, and the frequency got back normal, the voltage got back normal with any of the control modes that were discussed. The next test that was performed is the loss of last synchronous generator. So basically, it's the same test as previous. We have the island, but on top of it, we also disconnect the last synchronous generator. And now we can see that the recovery process is much more difficult. It takes more time, and the deviations of the frequency and voltage are much larger. So if you take a look at the figure on the left, you can see that it takes much longer, and the deviations are much worse, let's say, than in the previous case. However, at the end of the day, we still go back to, let's say, stable operation. So to mitigate this problem, the thing that they tested is to increase the capacity of the converters, and instead of 150, they were using 200 MVA rated converters. The initial power flow was still the same, 100 megawatt at each of the converters, but then just because we have more capacity during the transient, the converters can contribute more to the stability of the grid, and we stabilize much faster than before. All right, so this is basically the overview of the paper that that we did. Some conclusions. I guess this is not going to be a surprise for anyone here in this session that yes, grid forming converters can positively impact the dynamic behavior. So it's all very good. We all know that. They also identified, let's say, based on this study, that the share of the grid forming converters that allows to keep the system stable is around 15%. Then we have seen, depending on the capacity of the GFM converters, the recovery process can be slower. It can be more difficult to recover. The conclusion that is probably more for the CEN is that they actually need these enabling technologies. In fact, the HVDC transmissions, the grid forming converters to improve the operation of their grid. And of course, during all the studies that you have to perform, you need to use good EMT tools to assess the behavior. And one last slide here is going to be that the conclusions as the next steps for the CEN to do more research, to validate the results with the vendor models and test behaviors in conditions where we have even more renewable generation. So thank you very much for your attention. Okay, then yeah, okay, this is going to be for the next presenter.
Right, so we're moving from Chile to down under, and we have a presentation from Jarman Stevens, who is a co-founder of a company called gridmo, sorry, and he'll present on grid interconnection process in Australia and lessons that we can learn from there.
Thank you, Julia. Good afternoon. My name is Jarman Stevens. I'm an electrical and software engineer originating from Melbourne, Australia. Started my career at ABB in traction power, doing power electronics design and traction power systems, and eventually found my way into the power systems field doing grid interconnection studies in Australia. So I worked as a consultant and using tools like PSSE and PSCAD and Python to help developers navigate the grid connection process and do a whole bunch of studies. As Julia said, now a co-founder of a software company called Gridmo that integrates with PSSE and PSCAD and Power Factory to help engineers do those studies across different regions. And I've been in the US for about 3 weeks now, and a lot of people make the joke about all the scary animals that you get in Australia, crocodiles, spiders, and snakes. And I'll be touching on the scariest beast of them all, which is Australia's grid interconnection process. So to be divided into 2 parts, as I said, we'll touch on the lessons learned, but I was also asked to provide a bit of an overview of Australia's market, similar to Chile in a bunch of ways. The grid interconnection process, and also shed some light on, I'm learning a lot about the US market, maybe some interesting contrasts, and then we'll jump into some of the lessons learned from my personal experience. Australia is big, very big, but doesn't have many people in it. So population's about 25 million people. We have a collection of electricity and gas markets, and I think it was Ben from Fluence talking about microgrids, or very large grids offsite with mine sites, which I also don't like the term microgrid. In today's presentation, we'll be talking about the national electricity market. So it's the biggest market running along the East Coast. You can see on the picture on the right from far northern Queensland, travels kind of 3,000 miles, all the way down to Melbourne, across to South Australia, and punches an HVDC cable down to Tasmania. So a good way of thinking about it would be, think of a grid running along the length of the east coast of the US, kind of across to Texas, and an HVDC cable going to Cuba, all to supply only about 25 million people and demand that's less than the size of Texas. Some other fun facts: installed capacity is about 70 gigawatts, of which almost a quarter is rooftop solar. Most of the energy still comes from coal, brown coal in the south and black coal in New South Wales and Queensland. And then looking at the market mechanics, so yeah, think of it to be far more similar to Texas than Florida. Electricity price is established every 5 minutes. We've got a whole bunch of ancillary services markets and all that good stuff. This is the grid interconnection process. So I was going to go through each of the steps and dive into some of the detail on what's done. And this is coming from the experience of someone who's gone through it. I'll skip over some little bits and point out some of those interesting parts, having contrasted with US. So step one. So a proponent, I'll also define terms and acronyms as I get to them. So proponent, think of that like the developer, it's the term that's used. And they're putting together the idea. They've got a sparkle in their eye for a solar farm or a wind farm or a battery system. And they'll go through and they'll use hosting capacity maps. You know, they can be provided from the utilities or private companies as well, offer some software to help you put together the business case, looking at forecast electricity prices in different regions and ancillary service markets. An interesting part here as well is you can get the PSSE transmission network model from EMO. So you can't just log in and download it. You have to be a registered participant, which is a specific thing. You have to pay a bit of money. But during that early stage, the developer has quite a lot at their disposal to find good places to connect and trying to put together ideas and proposals that are not so silly. You're not trying to connect a 500 megawatt solar farm onto a rural 22 kV feeder. So in stage one, you can talk to the utility, talk to EMO, but yeah, you're kind of putting together that idea. By the end of that stage, you want to have something sensible. So step two, inquiry, and pulled up the acronym. NSP stands for Network Service Provider. So they can be a transmission network service provider or a distribution network service provider, the poles and wire people. So you say, I've got my solar farm, a wind farm, and I want to connect. And this NSP or the utility will give you back what's called a steady state data pack. And this is a collection of information, which might be more detailed understanding of how devices are switched to a nearby substation on where you want to connect, or more details on line overloading capabilities, or a bunch of more detailed information to help you make decisions about your plant. And the interesting part here is the responsibility is on the proponent or the developer to do the analysis. So they'll take that information back from the utility, the NSP, and then they'll do things like static studies at this time. So they'll look at a bunch of contingencies, they'll look at thermoanalysis, voltage stability, look at fault level. There's now starting to be some small dynamic studies conducted at this period, but they're putting together a report of how they think that this idea of theirs can be integrated into the grid. And the onus is on them that, if you need a runback scheme or something, they're the ones proposing it. So you submit that to the NSP, say, this is my idea, and their responsibility is to review it, make sure they're happy with it, it integrates well. And once you're happy, a few emails back and forth, then the end of this inquiry stage is the utility will go away to a different team and they will cost up, the plan that you've put together. What upgrades do you need? What's the length of line to connect, all that kind of stuff. And from a developer or proponent's point of view, by the end of stage two, you've got a good understanding of whether this is a bit of a go or no go for this project, right? You've got good understanding of your costs and what the return will be. So we're going through kind of a funnel of ideas and slowly whittling them away of the ones that you think are good. And if you're happy with it, you'll proceed to stage three, step three. So similar idea, you'll talk to the utility and you'll get a dynamic data pack. Ready for dynamic studies and a whole bunch of more data, and you need to put together an application. And there's a big checklist of things you need. And this is the stage in which, earlier we had people talk about the dynamic model acceptance test in Australia. That's where this sits. So you'll do generator performance standards, you do a whole bunch of PSSE and PS card modeling, put together a whole bunch of those reports. I can go into what type of tests they are, but I won't right now. But there's also other things. So you need to put together a single line diagram, a protection study report, a voltage control strategy. Are you operating in fixed power factor or voltage droop? If so, what power factor, what droop? So you're putting together this big application, and again, you submit it. And the same kind of responsibility is, the NSP and AEMO, their job is to review and be happy with that. But again, the onus is on the developer and the proponent to propose these standards. And at each of these stages you're going through, if you don't do a good job, it'll be thrown right back at you. If the model doesn't work or you don't propose something sensible, back it goes to you. It's your homework. So by the end of this application stage, you're happy, you've confirmed what performance that you're going to promise as a generator when you go get built. And at the end of this stage, the idea is to get a connection agreement between the proponent and utility, and this could be everything from the standards you promise to the costs of going out to build these things. I'll come back to this. An important kind of point at that is you become committed around this stage, is when other people have to consider you. So in stage 4, 5, and 6, very important, but maybe less relevant to this audience. But important things like building it, very important. But also you do a bit of modelling and also getting registered and set up to participate in the market as a generator. Jumping to step 7 and step 8. So this is about commissioning. So you've built the thing, you're going out to site. And you've done all your wonderful modelling and said how wonderful your plant's going to be and how it's going to do all these great things. And that's wonderful. But you've got to go to site and prove it. So you'll actually construct all the stuff and you'll do a subset of those tests you did. And then you need to overlay the results of what's actually happening on site with what you said that you were going to do. Now, you might be conducting thousands of studies, desktop studies earlier on, and you're not going to be doing thousands of studies on site, but the logic is you do a subset of these, you have kind of very stringent requirements on how accurately they need to match, and if the subset match, probably is high confidence in all the studies you did previously. Now, I'm still, as I've said, been here for about 3 weeks, still learning a lot about the US market, but some things that popped up in my head of interesting contrasts, let's say. One would be kind of that responsibility that I noticed is a lot more of the onus is on the proponent, the person applying, right? You do the thermal study, you work out what needs to be connected, and the job of the utility is really about reviewing that homework. Yes, it kind of clears the workload backlog, I guess, to an extent of the utility because they're not working through silly applications. Second thing of that kind of commissioning is very, very stringent. Another thing I touched on, that kind of committed status around the application. There's not exactly a rush in Australia to submit this early inquiry. You don't reserve a spot with that. It's that the date of you starting stage 2 is to an extent irrelevant. You don't reserve a spot and people don't have to model you. The point at which you get this kind of reserve spot and special status happens a lot later, once you've done a whole bunch more homework, and there's a much higher likelihood of you being connected to the grid. So you're not modelling junk projects above you that may or may not go ahead. If you've achieved this committed status, you've done a lot of homework here, spent hundreds of thousands of dollars, done detailed design. The likelihood of you going to get constructed is, it's not 100%, but it's very high. I won't go through all of this, but this is the AEMO, so the Australian Energy Market Operator, so the operator of the national electricity market. They publish something once a month, which I have to give an enormous amount of credit for. It's called the Connection Scorecard. And I highly recommend every operator and utility to do this because I'm a strong believer that to solve a problem, you need to deeply understand it. So they kind of opinion out, they just publish data on how long does it take to get from this stage to this stage, how many projects are there? And then from that, industry can work on solving problems. But 2 things I'll pluck out. One is there are 384 projects in the inquiry stage, and the amount of generation that represents is larger than the entire installed capacity in Australia. Big number. But again, to an extent, that's not really clogging the queue. The 385th is not modelling 384 people in front of them. So it's great, love to see the investment and we'll see those through, but that kind of same concept is not there. Second thing, talking about the length of a project. So it changes. Again, this is updated every month, so you can see how it's going. The average length of a project, you're looking kind of around the 30-month mark. And one thing I'll pick on, where a bunch of time is spent, is that application phase. So when people are putting together all of those studies, and why does it take long? Kind of looking at that picture on the left, to figure 3, looking around that 12-month mark of putting that together. It's interesting. Some reasons can be, there are a lot of studies to complete, right? It's a lot of work to get that done. Sometimes the quality is low, right? And the way that we're set up, if you submit something that's not up to scratch, you'll get sent back and you've got to go work on it again. As well, yes, you do negotiate particular standards and that can take time. And as well, we also have workforce issues. There's a specific skill set and we're still trying to fill a lot of roles. So that was the overview of Australia and its grid connection process. So jumping into some lessons learned, and now this is very opinionated. The first one is defining engineering terms when writing electricity rules. So I've grabbed this completely out of context, so don't feel like you need to understand every part, but it's part of the generator performance standards of what you need to do during a fault as an asynchronous generating system. So reading the first sentence, it's talking about how much current do you need to inject during that fault, and it's 4% of the maximum continuous current. Great. What's the maximum continuous current? And there was a lot of interpretation, and jumping ahead, eventually they did define it. They added it to the glossary, and it's a very specific definition of that current. It refers to another part of electricity rules, and if you are interested, it's kind of you looking at your constrained PQ capability that you promise at the point of connection of what you'll do over a certain voltage range, and it's that corner point, that PQ corner point of what the current is there. But the time between the first part being defined and that glossary coming in was years. And between that time, there was different interpretations. Some people said, well, it's the maximum. I'm going to look at the inverters of what they can do. And other people, that's silly, right? And I know it's picking on something which is maybe administrative here, but there was huge amounts of months lost of engineering interpretation. So defining those engineering terms, have a good glossary. That was something, and we haven't learned this lesson as well. There are new rules being made, where Gridmo made a submission to the Australian Energy Market Commission, basically saying the same thing of, can you please add this to the glossary? Lesson 2, again around standards. So putting standards together is a great process of making this more efficient and trying to avoid every generating system being bespoke. And the way that our generating performance standards are defined is whether it's, what set of undervoltages do you have to ride through to not trip? So taking that example, it's not like here's the curve and that's what you've got to meet. We kind of have the 3 classes of the standard. We have the minimum access standard, which is if you don't do this, you don't pass go. That is the bare minimum of what you need to do as a generating system. And then we have the automatic access standard, which is saying, well, if you do this or more, I'm not really going to ask any questions. Sounds great. And then you've got room to negotiate in the middle. And plucking an example here, talk to some people at the conference, we have what's the reactive power capability that you need to provide as a generating system. This is one of the clauses. So if you're a 100 megawatt solar farm, is the Q you're providing 20 megawatt, 30, 40? And that can be a detailed assessment, but the automatic access standard is it's 39.5 megawatt. And one of the lessons learned was the time spent that you could be debating whether it's 39.5 or 34.5 or 36.8 is the right number. The time you lose on your project is probably not worth just adding another inverter. Look at the engineering costs. That's quite interesting around our standards is a lot of these developers, and they have the right, they can negotiate, right? But they just choose, well, I'm just going to do this automatic access standard. Look, it's probably not so site specific, but I'm just going to pass go. Another one which kind of maybe ties a little bit into lesson 1 is this slide is showing, it's a plot of showing a Q step, PSSE and PSCAD overlay. Very, very simple dynamic SMIB test. But the point I'm trying to make is there are so many things that go into that. You're maybe 2 pieces of software, 2 different packages of software. PSSE and PSCAD is very common in Australia. You're looking at maybe data coming from site. You're looking at how to plot this. What channels do you want? What order do you want? What scaling do you want? There's analysis, and here it's calculating the settling time. How do you calculate rise time, recovery time? Talked at error bands. So the point I'm making here is something that's can maybe be said very simply as I'd like a graph with a Q step and show me the response and settling time. There's a huge amount of nuance that goes behind that. And what we've seen is it's very easy to write a rule with this, but what I highly recommend, and I'm talking to people in Australia about this, is run a phantom project. Run a 100 megawatt solar farm using WEC generic models on a 50 bus network. Just run it through the lengths of whatever rule to do. And then you'll find and discover a lot of this nuance that you probably need to define. Going back to that lesson 1 example of the define your terms, you would have had a team looking at that and said, well, I thought maximum continuous current was this. Well, I thought it was this. So if you're going to get the entire industry to spend trillions of dollars, put all this investment in, just run a blank project. Just run it through and learn a lot from that. And the last one. So I'll jump to the title, but point is when you're doing these types of studies in Australia, there's a lot. So you might have 500 dynamic tests. And what you're doing across dynamic model acceptance tests and SPIB, you're doing network tests, improving generator performance, there's system strength impact assessment guidelines, and you're doing it in 2 pieces of software. And then if you're lucky, maybe you're a solar and battery. So now you're looking at multiple scenarios. You're looking at solar only and charging only, discharging only, solar and charging, solar and discharging, the lucky 5. And you've got to do 2 submissions. So you've got to do a preliminary work and detailed work once more information comes in. And no one's perfect. So maybe you'll do a few iterations to get it right. Maybe you're doing tuning. So what's that? 1,000, 5,000, 10, so 50,000 tests, right? This is a huge amount of work. So there's a big software engineering task to just pump those results out. And going back to then to the kind of the title of the slide of, both are important. Software engineering and power systems are very important, but they're not the same thing. And kind of a lesson learned that we've seen is we had a big requirement for this modeling, and it is coming, right? And this is, we can kind of maybe canary in the coal mine on this kind of stuff. But you had a lot of junior engineers join the industry, and you had the layer of senior and principals who got all the great mentoring and couldn't do it when they went to sleep, right? And then the junior engineers were just tasked with, your job is to make plots. Your job is to pump out a whole bunch of things, and don't worry, I'll leave the engineering design to me. And that's a big watch out I've seen, where we're not really getting this transfer of information from the people who've been there and seen and built the grid to that next generation and building up that deep power system engineering knowledge in the workforce. Thank you very much. Excited to hear some of the questions. Thank you.
Thanks so much. So I think it was a great segue into Cynthia's talk, and we're transferring back to the US. And Cynthia Bothwell is technology manager and a grid integration engineer at Boston Government Services and contractor for US Department of Energy. And she'll be talking about a project that's near and dear to my heart, and I2X transmission roadmap. This was a project that was going on last year and wrapping up right now, and Cynthia will tell you the rest.
Yeah, thanks, Julia, and thanks for the invitation to be here today. And my background is electrical engineering, so I'm kind of the engineer on the I2X team. I worked 25 years in a past life in electric utilities. So I worked my way from field engineer to distribution planning to transmission planning to generation planning to integrated resource planning, pulling it all together. Load management was in there somewhere too. And so it kind of gives me the background of the utility. As generation, we were a vertically integrated utility. So I was kind of also a generation developer. So I also have that developer perspective. So that's kind of good for the I2X program. And after utility, I decided to go could solve problems that you couldn't solve at a utility. So I went into research and went to Baltimore at Johns Hopkins for my PhD, and then to the Department of Energy. So that's kind of my journey. And I shared that with you today because of the tragedy in Baltimore today. And I know things can happen in big groups, and I want to send positive intentions toward, if you feel comfortable, send positive intentions as a group to the Baltimore community, to the people who are working on the bridge or driving across the bridge, to the people in the vessels, and to the rescue workers, the first responders, and to the 34,000 vehicles a day that now have to find a new path to drive on around the Baltimore area. So I'm just going to give a brief moment of silence to send positive intentions. Okay, thanks. So I2X is a DOE program that's sponsored primarily through the Wind Energy Office that I'm part of and the Solar Energy Technologies Office. And we're hoping to have a faster, fairer interconnection process. while, because I'm an engineer and I did a lot with reliability, keeping the grid reliable and secure. And so that's very important aspects. We engaged national labs to help us with that. So primary to the roadmap that I'm talking about today was Lawrence Berkeley National Lab, and Will Gorman gave a talk and kind of previewed this roadmap at the fall ESIG meeting, and also Pacific Northwest Lab has helped with the transmission roadmap. And then we also have Sandia National Lab and the National Renewable Lab that are also partners in I2X as a whole. So a little bit more about the wind office and what we do. This transmission adequacy and access. So we're promoting some transmission planning studies. We just issued last week our Atlantic offshore wind transmission study. So that QR code will take you to a link to that study if you're interested. And somebody was asking me today about offshore wind platforms. So that's one that I had the great opportunity to visit last fall at Vineyard One. So that's kind of what a transmission substation for offshore wind looks like. We do grid reliability and resilience a lot that we were talking about, grid forming inverters and grid monitoring, grid stability studies. We do wind hybrid system studies. We have ongoing work on green hydrogen and how that couples with wind. And we also have a large portfolio, a growing portfolio on wind cybersecurity. So that's also important, and even including offshore wind and how to make that cyber secure. So things that are specific to that. So I kind of listed a few initiatives. We have an offshore. A big part of my work is these offshore transmission studies. We have HVDC FOA that we accepted proposals or announced projects for last fall for developing HVDC standards, developing functional requirements for HVDC, so the multi-terminal interactions for DC. We've heard some of those kind of talks today. And also education for offshore wind and for engineers to understand how HVDC and offshore wind work together. We also have a currently open FOA on innovative designs for HVDC converters. And we just heard in the last session, if you were here, on wind data or data overall needs. And so we did something on wind production data too there. Okay, so I'm talking too much, so I gotta move on. So the graph on your left is a sneak preview of the queued up report that's done by Lawrence Berkeley National Lab. And it's the will be the 2024 edition, but on 2023 data. And so this is comparing the wind queues in the US from 2010 to 2023, and also comparing that to the installed capacity, all the total installed capacity on the grid. So we can see a significant increase over the last 13 years of how many projects are in the queue. And then the relative comparison of how much is in the queue versus how much is existing on our system today. So sometimes people don't realize how huge this problem is. So that's just a kind of gauging that. And then the graph on your right is just the four pillars of the I2X program, which includes stakeholder engagement, data analytics, which the queued up report is part of, technical assistance, and then this roadmap that I'm going to talk more about. We started off kind of the stakeholder engagement and education session through solution exchanges. We held 22 solution exchanges. They ranged from workforce, engineering issues, economic, like market and economic issues, and I said workforce, equity and fairness issues. And we had over 2,000 participants from 350 different organizations participate in those and weigh in on some of these issues. And that helped kind of frame some of our thinking about this roadmap. And the roadmap I'm talking to today, I didn't have it on this slide, is transmission only, bulk power system transmission. So some transmission is not considered bulk power system, and we're working on another roadmap for distribution and other transmission activities. Okay, so next we issued a draft, and it was vetted throughout the DOE offices, and then we socialize it to the public through a request for information. And thank you to any of you in the audience that might have participated in that RFI process. We had over 40 organizations, well split through industry organizations, 5 of the ISOs, and a very robust comment. And as a result of that, we changed, made some very significant changes to the report. So now a little more context about how to read the roadmap, which hopefully will get issued next month. It's in the final DOE process, which is a lengthy review process, as probably any of your organizations go through. But we have short-term solutions, which are things you can start today. Actually, most of our solutions are things that need to start today, but some can be implemented and complete within the next 1 to 3 years, while other ones are more long-term and might take 5 years to gain traction, or first you have to do fundamental analysis and then move those into like a pilot and test those. So we have them segmented in the different time categories, and then we identify different solution actors. So unlike other DOE roadmaps, this isn't just about DOE. This is about the whole interconnection community and how each and every one of us can help improve the process to reduce that queue or get projects through the queue faster. So we've identified all these entities. You might not see consultants up on the list, but that's because consultants serve a variety of communities. You could work for utilities, you could work for developers, you could consult to regulators, or your firm can consult to all 3 of those or more. And so consultants kind of fit into what mission space you're, what type of clients you're serving. Okay, so I don't think we went over in the fall this, the metrics we're using. So I'm going to spend a few minutes on that. So what we had in the draft were kind of maybe reasonable metrics based on historical data. After after the draft roadmap was released, we did some stakeholder presentations, and we did kind of like a questions, facilitated kind of talking through, are these the right metrics? Are they too high, too low? What do you think? And based on that feedback, we had originally had 5, we reduced it to 4. And we made the goals more aspirational. So you're going to see some pretty tight targets that we've set for 2030, because that's what the ODE does. We do the earth shots, the moon shots, and we try to go for aspirational things. So first is the reduced interconnection time process. So that's from the time you enter the queue to the time you have an interconnection agreement signed. And so each of these is important because you can make time measurements at various parts of the process. And so that's the first one. Current average or most recent average was 33 months. 2 ISOs said they can do it in 12 months or less. So we decided that would be a great aspirational goal. And compared to where we are today, you could see that's very aspirational, especially considering how many projects are backlogged in the queue. The second one is to lower cost uncertainty. So the one we omitted was to lower costs. There's just so many moving parts with supply chains and inflation, and as the best spots on the system get used up, of course, things are going to get more and more expensive. So that was a really hard metric. So we went with lowering cost uncertainty. So when developers are provided with the cost, we hope that then the true cost at the end of the project is within that $150 per kW difference from what they were kind of told up front. And a current benchmark price for that was $551. So again, We think it can be done. It is an aggressive target. Next is increased late stage completion rates. So this is another one that kind of changed from the draft roadmap. We kind of had all completion rates. We're trying to, as for 2023, which I didn't mention, I'll come back to that, but they're kind of looking at how can we reduce speculation in the market. From our perspective, we know the market needs to have more projects than get built because that provides a sufficient market for the customer to choose a renewable project, a clean energy project. But we don't want too many that it overburdens everyone. So we also talked about having this one greater than or less than something and greater than something else. But we settled on, we wanted late stage completion instead of all completion. So that's from the facilities, when you enter the facilities study process in the US to, again, when you are commercially operational. And so again, a different time frame segment that we're studying here. And we wanted that to be over 70%. And today we're at around 45%. And you can see that metric goes back to 2016. And the reason for that is because a lot of projects that have started after 2016 are still in the queue. So they're not withdrawn and they're not completed. They're just still in the queue. And so you can't really benchmark any later than 2016 because there's not that sufficient number of projects that are either withdrawn or completed. And then the last one is to maintain system reliability. We did this one specifically for Julia, and it should have your name on it. But as many of you are aware, we've had system disturbances due to either inaccuracy in models or not actually having studied that or having settings done incorrectly and not measured. These are totally preventable. And so we, reading through NERC recommendations from those disturbances, we all decided these are all preventable. And so our target's 0. Okay, 5 minutes. Okay, so we might not get through specific solutions, but that's good. So we also have this thing about 4s. So we had 4 pillars for I2X. We also have 4 goals for the roadmap, and these will be the same goals in our distribution and subtransmission roadmap to increase data access and transparency. And so that's around making data available, but also considering, in our cybersecurity team at DOE was also adamant about this, it has to preserve critical energy information and competitive information. And so how to navigate through having that data transparency while also preserving those aspects. Second is improving process and timelines. So that's more of the administrative process kinds of things. How do we manage the queue? How do we coordinate with affected systems, adequately to do affected system studies, that inclusive and fairness in the process, and also workforce development we included in the process section. The third one is promote economic efficiency. As some people said, it might not be least cost, but it needs to be an efficient use of dollars. So some people say just, build transmission lines everywhere and have the utilities pay for them. Well, is that fair to the retail ratepayers that then have to pay for all that infrastructure that might be underutilized? So we can't necessarily do that and preserve rates. That wouldn't be efficient. But we also need to figure out fair cost allocation methods. So those are, again, some of the things we're struggling with there in the tension you'll read in the document between those activities, having a robust market and having the right cost allocation. So that's cost allocation. Transmission planning, that was another aspect I didn't mention before that changed from the draft to the final is there is a connection. We knew there was a connection, but we were like, how much can we tackle in one document between transmission planning and the interconnection process? So we tried to increase that a little bit. It's not a transmission planning solution document, but we've tried to put more ties there to that transmission planning aspect. And then the last says maintain reliable and resilient and secure grid. So I kind of already talked about that, but it's about modeling and tools and then also development of standards. Okay, so this is a sample solution on developing tools to manage, analyze, and visualize the transmission interconnection data made available in 2 of the other solutions. And so you might say, oh, that sounds like FERC 2023, but this goes beyond that, beyond hosting capacity that they have in that order. And so we're looking also at dynamic stability issues and if you're not familiar, and I'll have a QR code at the end of my talk, but we did issue a FOA last week. And so one of the topic areas in that FOA is a funding opportunity announcement from our, again, the joint offices and I2X for doing just this and developing tools that will help make this data transparent. So I invite you all to participate in that funding opportunity, especially utilities and software developers that would help with that. So you can see, again, the actors of variety from utilities and software vendors and the research community and then across the different areas. So I'm going to skip over because I'm almost out of time. To another one in section 4 under the pillar 4 on reliability. And that's about EMT models. So they're very important to the interconnection process and how to make those, again, faster and how to understand when should we use them. So we don't want to go over, we know EMT models are going to be needed for some aspects of the system, but maybe not across everywhere. And so we don't want to go overboard and say EMT must be done anywhere, everywhere, and make the process even longer and have engineering shortages even bigger. So part of it is figure out when should we run EMT studies and when shouldn't we? And then how can we make these EMT studies faster? So that was the second prong of the FOA that we issued last week, was to address those needs. So wrapping up, you know, where do we go from here? There's the FOA that I've been talking about, another QR code that you can, that'll take you to that funding announcement. We're going to talk at other engagements such as this. And so if you have an event coming up and you want someone from DOE or from one of our partner labs to come talk at your event, we'd be glad to do that, to talk about how we can start implementing this. And then a very exciting thing that I wanted to kind of kick off today, and Julia is going to talk about it more maybe later, is we are kicking off a something for standards, and it's a standards implementation forum, if I got the title right, or she can change it. And it's kind of like a DOE convening, and it's around getting best practices, sharing like a community of, I like to call it a community of practice, but around disseminating ways that we can adopt these standards and get them into practice. So there's a big standards development effort, which is great, but then you have to get them into practice. So that's going to center around that. So I'm going to end there, and thank you.
Thank you, Cindy. So we'll continue around generation interconnection in the US, and Sarah Toth, who is a senior associate at Rocky Mountain Institute, will present on near-term solutions to new generator interconnections. So this is a little bit around those solutions that are in the roadmap.
Yeah, thank you, Julia. My name is Dr. Sarah Toth. I'm with RMI, and I'll be talking about some near-term solutions to new generator interconnection, primarily in the US. But I want to give a little bit of a background about RMI. We're an independent, nonpartisan nonprofit working to accelerate the energy transition affordably, reliably, and equitably. And we do that through our Think, Do, Scale model. So we're kind of like a think tank where we identify solutions, we try to implement them, and we try to leverage global market buckets like finance, technology. These are catalysts that could push implementations of solutions past a tipping point to scale them globally. So within RMI, I'm on our carbon-free electricity program. Our change model within that program is to align capital and incentives with solutions for deep decarbonization. In today's talk, I'll be talking about two different topics. One from utility transition finance, which is to support utilities in utilizing financial solutions to transition their fossil assets and invest in carbon-free electricity. And another of which involves grid enhancing technology, so emerging priorities to enable interconnection. Why? Well, like Cynthia just touched on, there are a lot and an unprecedented amount of new renewable energy in US interconnection queues. Not all of them will get built, unfortunately. There's a lot of wait time in the queue, and it takes years to build the new interregional transmission that we sorely need in the US. But we must also deploy solutions in the near term that can help bring more clean energy online. And to do this, we have to make the best use out of the existing grid that we have as we can. So to that end, I'll be talking about grid enhancing technologies and clean repowering. These are complementary solutions to that long-term interregional transmission build-out need. The first is the novel thing about the work that we did is primarily grid enhancing technologies are considered operational tools, but we really wanted to apply them and pressure test them in the planning paradigm for interconnection. And these include both dynamic line ratings, power flow controllers, and topology optimization. Then I'll be talking about two types of clean repowering, surplus interconnection service, and generator replacement. And I'm curious because in the last fall workshop, about half of the audience had heard of GETS and half had not. So I'd like to get a show of hands. If you have heard of grid enhancing technologies before, raise your hand. Oh, that's quite good. I think we're making improvements. Okay, great. So let's talk about GETS first. If you don't know about GETS at a glance, here are some good analogies. Dynamic line ratings, or DLR, the transit analogy there is like real-time adjusted speed limits that in inclement weather, you should drive more slowly, but in really good weather, you could probably safely drive faster. So these adjust the carrying capacity of transmission lines based on a real-time weather measurement. Another is power flow controllers. The transit analogy here is like railroad switching stations that would direct trains to free tracks, or they push power away from overloaded transmission lines and onto lines with spare capacity. Topology optimization, finally, is a software-only solution that can automatically reroute power flows around congested areas. And as Pablo likes to say, it's like Waze for the grid. So like Google Maps as well. What we wanted to do is emulate PJM's own interconnection study methodology, and particularly the feasibility study portion, because we wanted to have a really rigorous analysis that RTOs and utilities could emulate. So to do this, we contracted with Quanta Technologies, who's a well-used industry organization that regularly conducts these sort of interconnection studies for utilities and RTOs. In scope were the three types of GETS that I spoke about, 5 of the PJM states, 3 future years, and 3 grid conditions, summer peak, winter, and light load. And unfortunately, we couldn't do more than that because already that was a really large scope. And on top of the power flow modeling of just getting the PSSE models from PJM, what we did was add all 126 megawatts 126 gigawatts of generation from PJM's transition cycle 1 into the power flow model. and we did contingency analysis to assess thermal overload violations. And so then we whittled down that large pool of projects to try and identify on which ones would grid enhancing technologies really help get interconnected. And for that reason, we stuck with about thermal overload violations of about 10 to 20%. So if a new generator were to come online in PJM's transmission grid and trigger a 10 or 20% overload violation, we assessed whether we could alleviate that violation with grid enhancing technologies. After that power flow modeling, we also conducted production cost modeling, or the 8760 economic dispatch analysis, to quantify the cost and emissions benefits from those grid enhancing technologies and new renewables. So how did we do this? Like I said, it's very new to apply grid enhancing technologies to the planning paradigm. So our approach was to do a deep dive analysis separately for every single grid enhancing technology and have that inform how we were to apply them to our power flow modeling. For example, for DLR, we chose multiple locations on the PJM grid and had a vendor conduct a deep dive analysis at all of those locations to reveal what the uprate would be at every hour of a representative day of every month out of the year. And so those were really interesting findings. I'll just report that we found an average of 17% uprate in summer peak conditions. So a lot of people think, well, how much can you really get during summer? But that was just the average. So a lot of times it was even higher than that. But we wanted to be really conservative in our application. So we only allowed a 10% uprate to represent DLR. With power flow controllers, it was a little different. We were able to model power flow controllers in PSSE with a dynamic reactance to adjust the line's impedance. And that was able to optimize and select the number of and placement of power flow controllers in the study. Finally, we worked with NewGrid to conduct a deep dive analysis of some overload cases to figure out where topology optimization is best suited to address certain contingency conditions, like the NERC P0 through P7 contingency conditions. And we gave topology optimization credit for P1, P2, P4, and P7 conditions. So we wanted this to be a really replicable approach that could help other operators and utilities incorporate GETS reliably into their planning models. So what did we find? Well, we found that just 95 GETs in this 5-state region of PJM could enable 6.6 gigawatts of new clean resources to come online by 2027. And on this graph on the left, you'll see that we assessed each grid enhancing technology, both individually and in combination. So topology optimization, power flow controllers, and DLR, and then that combined bar is the 6.6. So in some cases, they cannibalize the ability of the other to address the same overload, and in other cases, they're very complementary. This amounts to about 5% of all queue generation, mostly solar and storage. Not only that, but these grid enhancing technologies are much cheaper, millions of dollars cheaper than the traditional or conventional network upgrade, which would be to reconductor or rebuild a transmission line. So we did a cost comparison for in each of those cases where power flow controllers or dynamic line ratings or topology optimization were applied. And the savings for developers are really, really large. Not only that, but to pivot to the production cost savings a little bit, the savings for consumers are also very large. So we found that once online, the production cost savings as formulated here, JM, from grid enhancing technologies and the new generation that they enabled could total $1 billion per year in savings, compared to a $0.1 billion or $100 million cost to install these 95 grid enhancing technologies. And these savings are driven both by the lower operating expenses of the new renewable resources displacing fossil fuel generation, and existing renewable generation already on PJM system benefiting from the reduced congestion due to grid enhancing technologies. And also every year, as a result, carbon emissions are also reduced. So GETs are applicable in a planning paradigm. We can model them and deploy them reliably, and we think they're really complementary transmission solutions that could help us get more clean energy online in the meantime. I will pivot to clean repowering now, which is another way we can try to get the most use out of our grid. So what we term clean repowering is deploying clean energy at existing fossil fuel plants interconnections. And this is an umbrella term that encompasses both surplus interconnection service and generator replacement. So in the middle diagram, you can see that surplus interconnection service is when you add new generation at the site of an existing plant that would continue operating. And generator replacement is adding a new generation unit at the site of a retiring unit or plant. And there's two IRA or Inflation Reduction Act incentives that improve the economics for these cases, like the energy community tax credit bonuses and the DOE energy infrastructure and reinvestment loans. First, a little bit more about surplus interconnection service. These are governed by a federal standard, FERC Order 845. And you can see in this little map on the right of the US that most of the US has a surplus interconnection process unless you're the country of ERCOT or the New York ISO, which received a waiver. And the key components of this service is that priority is given to the existing generation owners. There are no network upgrades allowed, and you must not exceed the total interconnection service of the existing plant. So if it's a 100 megawatt plant, you can't put a 200 megawatt solar farm for surplus interconnection service. And if that facility retires, the interconnection rights of the surplus facility will also retire within 1 year of that facility retiring. In comparison, generator replacement process are separate from the queue and not governed by a federal standard. In fact, MISO set the standard in 2018 with its generator replacement process that many other RTOs have since copied. And the map looks a little bit different. There's some teal, there's one place where generator replacement processes are pending, and that's in PJM. And some places like ERCOT do not have a separate generator replacement process. The key things to note here are that these requests for generator replacement must be made at least 1 year prior to that plant's retirement, and new generation must come online within 3 years, which is actually a very tight window for developers. Also, the initial process also included restrictions on plant ownership, but those have been amended and relaxed over time, but they differ region to region. So what is the improvement of these two fast track type processes? Well, they reduce interconnection study timelines and costs. So on the left, you can see the x-axis is months. We have about an average of 4 years typically for interconnection these days, even though it's supposed to be around a year and a half. With replacement and surplus interconnection service, those processes are much shorter and curtailed compared to the normal standard interconnection process. So you can get through a lot faster. And then with costs, the standard interconnection costs are in the hundreds of thousands, whereas for generator replacement and surplus service, it's much less. Let's talk about the EIR and how that utilities can utilize the EIR and low interest debt from the EIR to pull forward reinvestment in clean energy. So there's two examples I'll walk through to compare. And on the left, we start with a 1 gigawatt existing asset, a fossil fuel plant that has a $400 million unrecovered balance. And first in this top row, we will think about traditional financing at which in 2031, they have to look toward reinvestment. That plant balance of 400 million is going to be paid off through rates, probably at a 6.6% rate of return. And then they'll build new solar and storage in 2031. And you can see a little tabulation on the right-hand side of the 2025 costs to ratepayers and utility earnings, as well as the 30-year net present value of that choice. On the bottom, we have accelerated reinvestment with the EIR in 2025. So instead of paying off that balance through rates, the EIR refinances the uncovered balance over 30 years. And then in 2025, the new solar and storage can be built with partially refinanced EIR debt. And actually that not only increases utility earnings, but reduces ratepayer costs, both in the 2025 case and the 30-year net present value. So it's actually a big win-win for both the utility and customers and emissions. In terms of the scale of this opportunity, we find that it's about a 250 gigawatt, no regrets options, and it can reduce system costs by about 21 billion over a 30-year planning horizon. So not only are we avoiding the high cost of fossil fuel use and new transmission build, but we're reducing interconnection costs. And you can see those savings in this top chart. The green is that 21 billion in net present value. And on the bottom, you could see the annual deployment of clean repowering for solar, wind, and battery energy storage that we've projected out into the future. The other really great thing about this is that you can help minimize the grid impact of new generation and retirements. In a lot of cases, a retiring unit, we might have to keep it online because of some weak voltage in the area or something like that. But if we aren't able to replace it with a grid forming battery and provide those services in another way, it could be a great way to minimize the risk there. And in addition, there are some other resource adequacy issues if you just start retiring generation without replacing it as our load continues to grow. So clean repowering is happening. There's a growing number of projects nationwide. Vistra replaced its Moss Landing gas plant with 750 megawatts of 4-hour battery storage. Elevate Renewables is deploying storage at some natural gas facilities. There's a lot of really great examples. So we do think that with IRA, the time is now to look at uneconomic or underutilized generation and consider this opportunity. Clean repowering can support the faster interconnection of clean energy resources. The IRA incentives make this even more economic for utility owners. And then this helps us get the best use out of our existing grid while minimizing reliability risks. So of the two projects I talked about in both the GETS and the clean repowering work, we were limited in scope to only steady state thermal analyses. So we know that impacts to voltage and stability are also important, but the dynamic analyses were prohibitive because of the large scale context of both of those works. So in our future work, we do hope to analyze whether advanced or grid forming inverters can also help expedite interconnection and support reliability. And please reach out to us to get involved in that. So thank you so much.
All right, so last but not least is Chief Engineer from Energy Systems Integration Group, Julia Matevosyan, who will be talking about inverter-based resource interconnection requirements and latest developments of that. So I'll talk about, maybe just hold this. Oh, okay, thank you, Sarah. I'll talk about standards, so it's related to interconnection process and beyond. You had a lot of slides. All right. So Cynthia already mentioned a little bit about importance of standards. I have this history lesson here. And I remember all of this happening in 2000s, early 2000s in Europe. That's when they started looking at interconnection requirements for inverter-based resources. Initially, each country looked at interconnection requirements in their own country, and was all in different languages even. The first harmonization efforts took place in 2007 in Scandinavian systems, because they realized that systems are interconnected and they need same standard for all resources there. And same happened in Germany in 2008. First requirements for interconnection of inverter-based resources appeared in Texas. And then some iterations happened in the next 5 years between all of those places that had interconnection requirements developed. In 2015, that's when first NERC PRC standard was developed, and it had right-through requirements. But this first PRC standard was protective settings requirement rather than interconnection and performance standard for IBR. Then in 2016, that's when Association of System Operators in Europe came together, and they decided they need to harmonize all of the interconnection requirements that were produced by different countries and have it harmonized on European level. So they worked for a while, and then I believe in 2016, that's when they came up with the requirement, and then in 2019, that's when it got implemented on national level. So now in the entire Europe, there is a unified harmonized standard for interconnection of inverter-based resources, and they actually have it also beyond transmission level, and that relates even to smaller inverter-based resources. So that took 20 years to get this harmonized effort done in Europe, but here in the US we still don't have harmonized interconnection standard. It still differs region to region. Some regions only it's as basic as pro forma for LGIA. In some regions there are more stringent interconnection requirements, but we need kind of harmonized interconnection requirements across the US because this is, one power system or 3 power systems, but anyway, performance of IBRs is kind of important equally to all of these regions. And I think where the need for this unified interconnection requirements is obvious is the SNERC disturbance events that's been happening, or at least been reported since 2016. What you see on the chart here, these events and yellow, this is solar tripping that is for normally cleared fault, then solar tripped unexpectedly on multiple resources. And then the last event happened in 2023 in Utah, 2 big events in Odessa, Texas, and that's what you see in the left-hand side, the table from one of the Odessa events. So this is chart from ISO that I quite like. So they took, I basically put this all events together on one plot, but they went one step further and they looked at causes of tripping of inverter-based resources in these events. And you can see that some of these causes are pretty common. So momentary cessation, slow active power recovery after fault got cleared, AC over voltage protection, tripping IBRs, and this is because of reactive current injection that is too aggressive after the fault is cleared. It's not removed fast enough and results in over voltage and then tripping of IBRs. So all of these things kind of commonly happening since 2016 through 2022, 2023. And we need to do something with requirements for interconnection of inverter-based resources, but also with how we assess inverter-based resources during interconnection process to make sure that this is not happening. And Cynthia has this 0 event aspirational goal from DOE roadmap, which I think can be achieved with good detailed interconnection requirements, but also process for conformity assessment that these requirements are actually being met. So in 2022, in April, there was IEEE 2800 standard that was approved and published on the Earth Day, actually. And this is a IEEE standard for connection of inverter-based resources to transmission, sub-transmission level, and it defines performance requirements at the interconnection point. This standard was developed by more than 175 working group members. These are SMEs from different sectors of the industry, manufacturers, developers, system operators, transmission owners. They worked on the standard for more than 2 years. It had really high approval rate, more than 94% approval, and more than 90% rate of response. The only problem with it is it's really good comprehensive standard. The only problem with it is somebody has to adopt it for it to actually apply. So now as the standard got adopted, approved, now different areas are undertaking steps adopting the standard. So I stole this slide from Jens Böhmer from EPRI. And you can see, first of all, 3 different types of adoption, but also which areas are adopting and in what type of adoption they are undertaking. So general reference adoption is basically thou shall be 2800. People just say, in the interconnection rules, they say 2800 now applies to all IBRs connecting at transmission level. And this is it, and no more words there. Detailed reference is where there may be already existing interconnection requirements and they adopt certain clauses of 2800 and refer to these clauses in the respective documents. And then full specification is basically looking at your own interconnection requirements and borrowing some language from 2800 and adopting it into the document. So it's a kind of more work, more manual. And yeah, so in green, you can see some areas that are already adopted. So this process finished there and it's now 2800 applies. And then in yellow, you see areas that are still working on it. And in black, some areas that I heard are working on it. It may be a little bit outdated. This has been updated in fall last year. So if you are in green already and you're not on this chart, don't be offended. So looking at how people are adopting it, I thought it's an interesting chart to bring in for maybe those who are considering adoption still and talk about how the process is actually going. So basically entity decides to adopt 2800 and the next question is, do they already have comprehensive interconnection requirements in the area? And if the answer is no, then the path is easy. You just adopt 2800 by sorry, it's the other way around now. I have a typo here. So it should say general reference here. So you adopt by general reference, you say thou shall be 2800. Then later down the road, you make a decision from when it applies. So from which interconnection date that inverters now have to be 2800 compatible. And then the reference document is published and refers to 2800. Primarily, when this adoption path is taken, people also are waiting for 2800.2 publication. So 2800.2 is a guide for what 2800 actually means and how to verify conformity with 2800. So they are basically requiring 2800 now, but they are saying we'll wait until there are procedures about evaluating it. So it's basically we trust your word to say that it's 2800 capable, but we'll test it at a later stage. And then if existing comprehensive requirements do exist, then there are two different paths available. So either you do by detailed reference, so basically refer to clauses of 2800 in your documents, or you rewrite full specification and basically adopt some language from 2800 into your own documents. Usually when these two passes are taken, then there is some gap analysis going on because you already have a detailed document that you need to understand where there are gaps. And then prioritization is made. So basically you decide which of these requirements are most important to implement first. Again, decision on applicability date, and here it may be differentiated by requirement depending on which requirements are more difficult to implement. Those will be pushed a bit further. The ones that are easier, lower hanging fruit, will be implemented maybe immediately. And again, the documents that entity already has will now include either references to clauses of 2800 or specific language that is borrowed from 2800. And in these two paths, we can see like different ways that people develop their own verification procedures and leveraging some existing verification procedures that they already have, or they decide to wait until 2800.2 is developed. So this is kind of three common paths that we see. And so if you are one of the utilities that are thinking about adopting, maybe you can choose one of these paths to follow. And so this is just one of the examples. MISO is currently in the process of adopting 2800. They are doing by detailed reference. So basically for clauses of 2800 will apply to where they see gaps in the existing interconnection requirements. And so phase one has been complete already, where they looked at voltage ride-through, fast reactive current injection, things like that. And now they are focusing on reactive range capability, voltage control, damping, primary frequency response, measuring and monitoring. So ERCOT is currently also undergoing kind of similar process. I just wanted to show one as an example. So I mentioned 2800.2. Just to repeat again, basically that's recommended practice to test and verify if inverter-based resources interconnecting bulk power system are indeed 2800 compatible. Currently, there are subgroups within this 2800.2 development process working on various pieces of verification. And this is split into type tests. So this is basically single inverters will be tested at manufacturer facilities to make sure that inverter itself has some capabilities that are compatible with 2800 requirements. Why am I saying this kind of complicated way is because 2800 applies at the POI. And so you cannot actually have 2800 certified inverter, because you can certify inverter all you want, but depending on how your plant is designed, the performance you'll see at the POI may be different. So manufacturers cannot guarantee that inverter that they sell will provide whatever you want at the POI. But they type test kind of taking these requirements into account, and the goal of this type test also to produce a unit model that has been validated. And then this unit model is used to develop a plant model. And then this is where design evaluation is happening. So basically, as you're designing a plant, you are making sure that all components of the plant are conformant with 2800 requirements. So there is subgroup 3 that's working on all of these pieces of how to verify conformity during design process. And then when plant is constructed and it's all complete, then there is as-built evaluation. So basically you're evaluating that whatever you verified in design evaluation is still the same. It didn't get changed. All the settings are being checked and models are being updated. And then there is commissioning and testing. So some of these things you can actually test in reality through physical tests. You do some model validation based just on this limited set of tests. And then there is post-commissioning monitoring. So post-commissioning monitoring part, that's something that is not happening today, even in areas that have stringent connection requirements. It's basically plant got connected and you forget about it until big event happens, and then you are wondering what happened. But with 2800.2, the idea is that you are continuously monitoring the plant, and say if events are happening, and it doesn't have to be a big Odessa event, maybe just your plant tripped once, now you have disturbance recording, and you can actually validate your models for large signal disturbance. And that is the first instance where you can actually do it. And you can also verify if your plant has been conformant with 2800, and you can continuously monitor the plant. And as updates are happening to the plant, some verification also needs to be done. So that's what the post-commissioning part is about. How much time? Oh, 5 minutes. So this kind of graph is showing what we have, kind of where the status is right now. We are finishing up language. We're hoping to be complete with 2800.2 by the end of this year, fingers crossed. But in the meantime, there are other things that are happening. There have been fork order 901 that I'll talk in a minute about. There are NERC standard revisions that are currently happening. Adoption of 2800 is happening. So once 2800.2 is complete and approved, all of this will kind of interlay with already ongoing efforts. So fork order 901 is basically directs NERC. It's been released in October last year, directs NERC to submit detailed standards development plan to address IBR reliability gaps in 4 areas. And this is data sharing, model validation, planning and operational studies, and performance requirements. And in response to this fork order, NERC filed a work plan in January 2024, where they detail how they're going to address this directive from FERC. And so basically, they prioritized these areas that FERC directed them to look at. And so the first priority is around disturbance monitoring, data sharing, performance requirements, and post-events performance validation for registered IBRs. And this is to be complete in November this year. And then the next priority is data sharing and model validation for all IBRs. Proposed completion is November next year. And the last priority is planning and operational studies requirements for all IBRs, and priorities November 2026. So I have two tables. I will not talk much about it, just like few words. So what is in this first bucket? They basically looked, and a lot of this work is already going on at NERC. So they already review some of the standards that are relevant for four-quarter. They are already under revision right now. And so they just basically bucketed this project by priority to address FERC directive. And so in red, you see the ones that are relevant more for IBRs. And this is write-through standard and data sharing after big events and performance of IBR projects where the standard development is being done right now. And then this is second priority. You can look at it. I will not go in details, just, you know, to save time. So I was thinking about how to conclude about all of this. A lot is happening, and this basically was the only thought in my mind. But then I thought better of myself and did this. So don't panic and carry IEEE 2800 standard and NERC work plan. Keep in mind that developers will build IBRs or any other plant only to existing minimum requirements. So to maintain reliability with higher shares of IBRs, we need comprehensive requirements, and we need to incentivize developers to go for equipment that has state-of-the-art capabilities. Adoption of 2800 can provide harmonized set of interconnection requirements, as well as enhanced performance of future inverter-based resources. It also provides certainty to manufacturers, so they don't need to design a project for each entity in the US, but they can just have one kind of a set of capabilities that is required across the entire country. FERC Order 901 recognized this need, and they are now working on this comprehensive interconnection requirements. They are leveraging 2800, which is, you know, I'm happy to see, because otherwise, if these new NERC standards are not aligned with 2800, then it creates a lot of mess, because many areas now already adopting 2800. So how do you realign this if NERC standards don't align with that? So I'm hoping that there will be good alignment. And having this audience here who is obviously interested in interconnection process, I would like to invite you all to participate actively in NERC standard drafting teams. Even if you're not a team member, you can join as an observer and you can provide your input during drafting of the language. IEEE 2800.2 is still ongoing. Participate. You can also review it once it's out for industry comments. And then NERC Inverter-Based Resource Performance Subcommittee is an interesting group where a lot of discussions is happening around reliability impacts of inverter-based resources, standard implementation, and so on. And it's not because I'm chair of this group I'm inviting you, but because it's really interesting. And yeah, as Cynthia mentioned, we'll kick off this effort on implementation forum. And the idea with this is actually this, so like to reduce the panic and provide most up-to-date information on existing standards, newly developing standards, and what does it mean to adopt the standards? How do you verify conformity and all of that? And with that, thank you so much. And we are ready for a question.